So thank you, Jeff, for the introduction. Thank you for the invitation. Also, thanks to Akash. So in today's talk, I'm going to talk about one of our recent work on what we call the brainstorming GANs. So I'll talk a bit, I'll spend quite a bit of time on the framework, and then I'll talk about the application to wireless. The application is simple, but I think it's meaningful enough. And I selected the topic based on the interest through the email of Akash and Jeff as well. So let me give a quick outline. I'll start by talking, just one slide on distributed learning and what we've been doing and how that leads to kind of this brainstorming GANs. And then I'll delve into the brainstorming GAN framework. I'll talk a little bit about generative models. My experience when doing these talks, sometimes some of the audience have not seen GANs before. So I'll give a couple of slides just to say what GAN is. And then I'll talk more about our framework, and there's extensive set of results there to show. Then I'm gonna apply BGAN to a small UAV communication network at millimeter wave. And there was an interest on another one of our work, which is more called Experience Deep RL. I'll give a quick glance on that, assuming I have time. It's gonna be just a couple of slides on that. Again, we all know about this shift from big data, which used to be the norm, towards small data, where you have multiple users or base stations as well that have small amount of data that partially represents the space that I want to learn in some sense. And this led, of course, to the emergence of federated learning. So federated learning asked, the first question they asked back 3 years back is, can users collaboratively learn a task of interest? But of course, that has grown much, much more since then. And we've started working on federated learning, I think, back around 2017. We looked primarily at two aspects of it. First, we went through, let's say, the path of least resistance, where we tried to look at how can federated learning help us communicate better, meaning do better resource allocation, particularly in scenarios where, let's say, you have VR users, you have users where predictions and proactiveness needs requires learning eventually, and there's a lot of distributed angles. And then we shifted a little bit to the reverse question. So what if I have a federated learning algorithm, let's say it's doing navigation or whatever task that it's doing, and it needs to use a cellular network. So when you communicate all these models and so on, and the figure here kind of represents that second view, they're gonna be subject to the bit errors, to delays and so on. So how can we quantify the communication requirements of a federated learning algorithm and beyond? And then we started moving more towards the algorithmic side of federated learning, and that got us a little bit into generative models. And the question is, how does federated learning look like if married with GANs or other generative models? So, I'm sure this slide, everybody knows it, but I'm gonna just have it for completeness. So as you know, there's these two aspects in machine learning. Either you look at the discriminative approach or the generative approach. The generative approach is typically more concerned with joint distributions, and that has, of course, a lot of applications in communications and otherwise. And most of the federated learning works, up to some point at least, we're looking primarily at discriminative or inference models, and we try to look a little bit more on the generative side. So there are many types of generative models, as you know. Perhaps the root of most of them could be back to the mixture models, the Gaussian mixture models, and also Bayesian networks. And there's, the two bigger fields there would be probably variational encoders and generative adversarial networks. So what is a GAN? A GAN is essentially a generative model that seeks to create unseen data. And oftentimes when we work on wireless, this term of unseen data, unseen environment comes back over and over again, especially if we're doing, if we're looking at the context that needs learning. And why it's called adversarial, I've had before folks thinking that adversarial refers to more of a security problem. The reason it's adversarial is in a GAN, usually you have a generator and a discriminator. The generator is trying to generate some data samples to kind of fool the discriminator, and the discriminator, as the name implies, trying to guess whether this is a real example or a real sample or a generated sample. And this actually gives rise to this zero-sum game, which is why it's adversarial. So you have a zero-sum game where the generator is trying to maximize a value function, the discriminator is trying to minimize that value function, and then you have to find an equilibrium of that game, and that equilibrium was established by Goodfellow's work as well, initially, of course, and that showed that GANs can work and they can realize all these fake data generation and so on. Now, the first question we asked was, what happens? Essentially, most of the GAN works in in wireless and in the machine learning literature, assume that you have a data space that is all known to your generator and discriminator, and then you're trying to model that data space and create a generator that can successfully generate fake samples belonging to your data space. But then we went back to the original question I asked at the beginning, right? So what if this small data is distributed across multiple devices? So I only have a partial view of the data set. I don't have the entire data set, but I'm interested in learning the entire data set. So all the existing GAN models, which are centralized, can be thought of as being more distributed. And here, a word of caution. What I will talk about is mostly the standard GAN, but of course you can change the framework and add to it info GAN. And there are, more new bells and whistles that appeared recent years. You can, of course, integrate those in what we did. So we said, what if the data of interest is distributed among multiple agents? So every agent has a partial view of the entire data set, but is interested in generating samples from the full view. What if it's scarce? So you don't have enough data. So distributed and scarce, actually, I explained them together already. And what if it's private? So you don't want to share the data. And again, in terms of privacy, what I'm going to present is just a small layer of privacy. If there are privacy gurus in the audience, I know you can do much better than what we did here. We're not going to claim that we meet the differential privacy concerns and things of that sort. So really our motivation was distributed, scarce, and a few other features, but privacy kind of came along as an extra benefit. So the question is, can we learn the distribution of the total data without sharing it and without relying on a central server that either has all the data or can receive all the data for us? So we started looking first at what's out there, right? Has this been done? So there were, I would say, three main state of art. I have seen recently some additions to those. They're variants of it in some sense. One is the the intuitive approach is, what about if we apply federated learning to a GAN network? So you have this FL-GAN where you have multiple workers. They have a generator discriminator, and they're gonna share their model updates just like in FL. They share the model updates for the generator discriminator with a parameter server. The parameter server does aggregation. There have been, again, extension with fedprocs and things like that, and then send it back to the workers. And they show that this kind of works well as well. The other, I think this predates FL-GAN, is this MD-GAN, multi-discriminator. The idea was, again, you have a central server. The central server has the generator. The workers don't have a generator. They have only a discriminator. So they exchange the discriminator output among them, and they exchange then back with the central server their outputs. And the central server, again, has the generator, generates the data, sends it back. F2U GAN is an extra layer on that. They just had some tweaks. If I remember well, they eliminated the engagement between the workers. So there's no inter-worker communication. And I think they had a different rule in how the generator updates. I don't remember exactly what they did for F2U GAN, but it was just a variant of MD GAN. Now, the problem with those is that they're not fully distributed, right? You still need the parameter server. That's still needed there. And they have expensive communication, particularly MD GAN and F2U GAN. FL GAN is a little bit better in terms of because it shares model updates, and there's some tricks that they've done there. And also, they cannot allow different neural network architectures. And why would we be interested in different neural network architectures? Because sometimes you have devices of different capabilities. So you might want to run a smaller neural network on one device as opposed to a larger one on another. So there could be kind of heterogeneity there. And they do not share their generators. They do not, own their generators, particularly in MD GAN and FU GAN. So the question was, can we create a fully distributed solution? So just the workers among themselves, they don't have a parameter server, where you can also have these heterogeneous agents and still along the lines of partial data and partial view. So this is the papers on arXiv now and submitted. So we came up with this brainstorming GAN. So the architecture is the following. We allow the agents to share their generator output. Basically, this is why we call it brainstorming. It's really the idea. It's not the raw data. It does reveal a little bit of the raw data, but it's still, you're not sharing the actual raw data set. And it's just like an idea of your raw data during the training. You share that each training epoch. And then we allow you to own your generator and discriminator. And then you have a local update, which is the standard local update at your own agent. So the benefits of this architecture, and we're going to show, I mean, a little bit of analysis more on the kind of like the game that comes that arises in this scenario. So the benefits is we don't need a central aggregator, and you can have different neural network architectures, and they can be capabilities tailored, as I mentioned. And you need less communication overhead. With a disclaimer here, I'll talk about it a little bit later. In some cases, I mean, compared to MD-GAN, F2U GAN, we're much better. Compared to FL-GAN, it depends on the dimensions. So we're going to talk about that later. It's going to be more efficient in many practical cases, but in some cases, maybe FL-GAN is less communication overhead. I'll talk about that later. So the theoretical formulation is, I mean, at the end, what happened here is we went from this just zero-sum game between one generator and a discriminator into a multi-person and player a zero-sum game between multiple generators. So you can see, if you're familiar, and I'm sure most of you are familiar.
Walid, are you going to return to that slide a couple slides ago that kind of, you went through that pretty fast, and I guess that was sort of the key new idea here. Yeah, that one. So,
yes.
So this is like basically kind of encapsulates the new idea of this brainstorming GAN, I guess,
yes.
is that everybody can have their own unique generator. So what exactly is like the message? I didn't quite understand what's being passed between these.
Yeah, what's being passed is you pass at every epoch, you pass the output of your generator, basically the generated fake, quote unquote, fake data. And once you do that, this will give rise to the game, and then the game will show that kind of this converges. And then in the experiments, we can show what the benefits would be.
Okay, but I mean, it's just conceptually, usually the generator is trying to produce something that's like high dimensional from something low dimensional, right? So is this expensive side information?
So it depends. It's not as expensive as some of the other type of information you would generate. It really depends on the data set. So for example, for a data set like AlexNet, it's less expensive than doing FL. In others, it's more. I mean, I'll show later in which. And when I say less and more, is compared to other distributed GANs. It's not.
Okay, so you're going to be like kind of spending some time now, kind of explaining a bit more detail how this architecture works.
Yeah, I mean, so the architecture, the idea itself is quite simple. It's we share the output of the generator, but that comes into the value function, and then that gives rise to the game theoretic setting that kind of extends from two-player generated discriminator among each other to an n-player game.
Okay.
Yes. So what is the difference here between the green arrow and the dotted arrow? Like that is also generated data?
So the green arrow is just the local update. That's that's just at the agent. So if we don't have brainstorming GAN, you only have the green arrow, and then everyone works independently.
Okay. Yeah.
I think what maybe Akash was asking is like the dotted arrow in principle could have the same stuff as the green arrow, right? It's the output of the generator.
True. It's generated from that distribution in some sense, but it's not the exact data point that you want.
Okay.
And
sorry, one last. Sorry.
Yes, go ahead.
No, I was just gonna ask you that. So you say they're sharing the output of the generator. So if I receive the output of other users, am I gonna use that as real data that I'm going to incorporate to my data, or how do you use that data?
Yes, I'm going to use it as part of the data that I'm receiving. So the way we do it is we're going to do a linear combination, basically, of the data I own and the data I get from other agents. There could be better ways to combine, but we showed that even with linear, it's kind of good as well.
Thank you.
Okay, so I guess this slide is, we went through it. So the theoretical formulation. So in the classical GAN, you have only this value function that's typically function of your discriminator value and of the discriminator strategy and the generator strategy. And then now you have these G, which are representative of this shared generated output from others. So J is the index, and I is the set of others that you're communicating with. And this essentially here you have the mixture of data. This PBI answers the question we just have. So PBI, I'm not sure if I put the equation on the slide, but PBI is basically a linear combination of your own data and the data that you receive from the other generator, which we call PGI essentially. So this is a mixture of the two, and they're weighted by a convex combination. And then you have the discriminator here as well. And so the generator aims to minimize this value, and the discriminator seeks to maximize it. And it's a zero-sum game, just like the original GAN. The difference is now you have multiple generators trying to do this, multiple discriminators trying to do this. And because it's interdependent and so on, then it's a very natural game setting. So formally, what they're trying to do, I mean, eventually after the training, what we're trying to do is to find these G1 to GN that minimize basically the generated distribution. At the end, my ultimate goal is to have every distribution of the generator at every individual agent, ideally spanning the entire data set, basically the entire data set of my information and that of my collaborating or my other agents. And then you have the discriminators trying to maximize the same value function. So the question is, first is can we find the Nash equilibrium of this game? Basically finding the optimal D and PG, which represents basically G1 to GN. So the theoretical results, I'm not gonna go through the steps, but just one step and then the Nash equilibrium. So first we can find the optimal discriminator. It is basically this PGI, which I mentioned in the previous slide. It's the probability distribution of agent I's generator. And PBI is this mixture of the two. Then with this intermediate result and another one, we can show that the game between the agents has a unique Nash equilibrium. This is the PGI, this is the PGI star, the distribution of my generator. It's related to the distribution of the data of my own and my collaborators, and there's a lambda here. So essentially at the end, in some sense, I'm trying to kind of model the union of these P data J's in some sense. This lambda, you can find it in closed form. I don't have it on the slide. It depends on how you communicate with your different agents. And it's basically a solution to a system of equations, which we have, in the paper. It's not very interesting to see the system itself, but you know that you can find that from that system. Now, if your graph is strongly connected, meaning every agent has a path to every other agent, all the lambdas will be greater than 0. And then you can kind of have a mixture of most of other agents. If not, the solution still stands. We still have the theoretical result still stands, but you'll not be as good as in the case to connect to others. So the communication graph structure affects quite a bit unit performance, and that we're gonna see how we're not gonna do optimization of that in this case. We're gonna do it a little bit more for the wireless problem, a little bit showing that there are things you can tweak. So there's a lot of aspects you can do better, right? For example, PBI, I mentioned it's just mixture. You can do nonlinear. You can do something smarter there. Also, in terms of the graph structure here, we assume it's an input, so there is a graph connecting the different agents in the BGAN, but you can, of course, do something more intelligent there. So I think the experimental setup will start to show a little bit more kind of how things work. We're gonna use different data sets. One which is just simple, just because it's easy to illustrate. It shows it shows the intuition behind the whole framework. It's not the most complex data set in some sense, but it's simple, which is this ring data set. So we assume that we have data samples drawn from a nonlinear combination of a gamma and uniform distribution, just a ring data set. It's just used for ease of exposition. In some cases, I'll show you the more like familiar data sets that like MNIST and CFAR in a few moments. Unless I state otherwise, I'm gonna use the ring graph, but in some cases, I'll use a kind of more complete graph also to show other results. So really this problem started initially with the question was, if you have two agents, I own half of the circle, you own half of the circle. Can I generate the full circle and can you generate the full circle? It kind of started with that very simple question, which is the question we answered here in some sense. So first, we're gonna use the JSD, the Jensen-Shannon divergence, as a way to quantify how good is the performance at the end. And here I'm showing, basically I show when I say 9 agents in this figure, I mean 9 neighbors. So that's 10 agents, it's my user plus nine neighbors. So we compare, so there's of course a trade-off. In an ideal case, you would have a single GAN that has all the data samples. And in that case, it's really the best you can do. And you can never beat that, right? If I have a single centralized GAN that has all the data samples I need. However, what we said is, what if I divide those data sets among a larger number of agents? Can we do better than not collaborating, than not sharing, than not doing brainstorming? So in this case, we can show that. So essentially, BGAN is a way to compensate for your lack of data. So we can see, for example, like a GAN with 10 samples, will have a JSD of 24, and you can do almost twice as better if you have 10 agents, each have 10 samples. Of course, you can say having more samples will be naturally better, but here we're showing that you can do it in a distributed process as well. It's not just a matter of adding sample. And again, we never claim we're better than a standalone GAN, because standalone GAN is, he has all the samples So we can do better, of course. In this case, we again compare the standalone. We have the BGAN with 5 agents and BGAN with 10 agents. On the y-axis, I have the number of data samples per agent. If you have 10 samples per agent, none of them are good, and that's pretty obvious in this case. If you have 50, you can see that the standalone GAN alone, I mean, here standalone is just alone. You don't have the whole data set. Barely can have part of the circle. BGAN is doing well in both cases. And you can see like it takes 500 samples for a standalone agent who cannot communicate with others to kind of find the distribution. But I mean, with BGAN, you can do it much faster, much earlier with smaller number of samples. And then we can also look at the JST again versus the number of neighbors and the number of data samples. Of course, again, back to my point initially, if you have all the 1,000 samples, turns out in this example, the 1,000 is kind of like a sweet spot. If you have all the 1,000 samples, you really don't need BGAN. I mean, you just use your own generator and you can approximate your sample or your distribution. But the less samples you have, the better it becomes with BGAN, and the better it becomes if you have more connected neighbors. And now here, when I talked about this different neural networks, so here we use the same neural network, but different a number of trainable parameters, basically. And that kind of, again, it's an implicit nod to saying that we have different computational, if you wish, computational capabilities per agent. So you can see that if you don't use collaboration, you don't use BGAN, then you cannot, I mean, reproduce the entire circle, and we're much better for all 4 agents in this case, 5 agents. I don't compare with MDGAN and FLGAN because it's just not possible. I mean, if that just doesn't work when you have different number of trainable parameters. Now, when the other question is back to this, you know, if I own half the circle, you own half the circle, what happens? So we're going to illustrate this here. I mean, of course, we show that for this 2 agent, it's a simple example, but they can generate the full circle. What if it's more complex? What if we have an MNIST database? So here I mentioned early on, here I use a more connected graph. It's not a ring, but it's kind of like we have more connection in the graph. You can see that the agent who owns the digit 0, after the training through BGAN, he can now generate digits 3, 7, 8, 1. And agent who owns digit 1 can generate 9, 3, 7, and 5, and so on. Now, the type of data you can generate depends on this linear combination, depends on the theoretical, basically, characterization we had. So you can do better or worse depending on how you do that combination, and also depending on the graph as well. So who is connected to whom and at which point. And another example now with the CFAR database. So you can see, for example, the agent who owns a dog image can generate a horse image, can generate a cat image, and so on. I think it's a little bit blurry, but you could see some of the different points that you're able to generate. So if you own airplanes, you can now generate also the cars from another agent. So the point of, I mean, this original point of having partial view and being able to generate an entire space seems to work well in BGAN. Now, in terms of the comparison to the others, to the baselines, and in terms of complexity as well, we're going to talk about that in a minute. So in terms of the JST, again, as a measure of comparison, the black continuous curve here is the standalone GAN who has all the samples. This is the best you can do, essentially. And it goes down because we kind of multiply by the number of agents, so as to keep the comparison kind of fair, quote unquote. If you do BGAN, you can see it's very smooth with the number of agents. You can maintain a very good JST compared to F2U GAN, MD GAN, FL GAN as well. And there's significant gains in terms of the JST, which essentially is accuracy compared to FL GAN. We can also compare the FID also as another metric. We can see that, again, BGAN is better in this case. And this is on the MNIST database. This is on the ring data set. But you can, I mean, you can do all these combinations. I don't show them here, and we did not run all possibilities, but you can see the same results. Now, in terms of complexity, so BGAN is, I mean, it depends on the number of agents, the batch size, and the data size. So MDGAN, and again, and F2U GAN, they depend on the batch size, data size, and neural network parameters. So these two are clearly worse than BGAN in terms of communication resources. The amount, I mean, the computational communication overhead you need to transmit. Now, compared to FL GAN, this is where things become different. So you can see the N is common, so it's proportional to the number of agents. That makes sense. In our case, it's proportional to the batch size multiplied by the data input. In the FL GAN, it's function of basically the model parameters of the generator and the discriminator. So it really depends. If Bx is greater than theta j plus theta d, then we're worse in terms of communication resources, or we're better in the opposite case. Now, when is that useful and it's not? It really depends on the database. So again, I mentioned the AlexNet. If I recall well, in the AlexNet, you need millions of parameters for FLGAN, and you need in the 100,000s for hours. But there are other cases where FLGAN would be better. But even in that case, in terms of accuracy, we are better. So we have another advantage. So that kind of sums up the framework itself. So we can show that partial data sets that are distributed can be kind of learned. You can learn the entire span of the data set of interest by your generator, and you can generate data points from that span. Now, what can we do next? There's a lot of things that can be done next. Again, you can enhance security and privacy. I'm not a privacy expert, so that's not an angle we looked at. But one kind of rule of thumb here, everything that enhances the security/privacy of a standalone GAN can immediately kind of map to BGAN. So whoever does an interesting solution to the privacy security problems of a standard GAN can map it back to BGAN, because we just use kind of the generator of a standard GAN. And you can also use the discriminator for inference. I've seen some works do that. They do it for a regular GAN, so why not do it in a distributed way? You can look at more sophisticated connectivity graphs and, again, combinations of your data sets and so on. There's a lot of applications. So we did an application to intrusion detection a while ago. That was closer to an MD GAN, not to BGAN, but I'm saying just more like distributed GAN. I mean, admits some interesting application in that domain. And of course, wireless is an application domain. I'm gonna present an example on a channel modeling where I'm trying to kind of find the spatial temporal distribution of the channel gain in a given area. And that kind of transitions to my next application. So in this application, it's a very simple model, and we tried just to focus more on the learning side in some sense. So we considered that we have UAV base stations. Why UAVs? Beyond the idea that UAVs, of course, they admit a lot of application domains, and they're more and more becoming common to transmit data in different applications. Also because UAVs eventually can move. So if you're in a UAV network, you're interested in knowing the spatial. If you want a spatial / temporal a map of your possible channel gains over an environment or a possible area. So in a UAV, I mean, you can apply the same for a standard base station, but UAV kind of is interesting in this case. We use a standard millimeter wave channel model here. I mean, I think everybody knows this. So we have the angle of arrival. I mean, everything denoted with R is the receiver, the user equipment I'm downlink here. T is the transmitter, which is the UAV in my case, and L is the number of paths. But we're gonna use the single pass channel. And this has a bit of a historical. Why did we choose L equal to 1? So we wanted to simplify things and to see if things work. And then it worked well with L equal to 1. Now you can use the same framework with a general L. The problem is in some of the optimization proofs I'm going to discuss in a moment, it becomes a little bit more complicated. But the general idea can still be applicable. So I mean, again, this is a general model. We just show the dependence on the spatial. XY is just the two-dimensional location of the user on the ground. T is time, and these are the angle of arrival, angle of departure. Sorry, and that's essentially a standard channel model. So these two slides, there's not novelty in some sense. It's just a step by step to the point. So again, doing the beam training on the pilot signal, we assume you know the AOT and the AOI and the AOD. Again, you can relax those assumptions as well. So we essentially what we tried here to do is separate channel gain to estimate the channel. So we're saying these UAVs are serving this area and they're estimating some channel gains. At the end, each one of them has a limited view on the channel gain for a subset of UEs at a given time in a given location. Can we at the end just learn the entire space, basically the entire distribution over X, Y, T, and alpha, which is basically the channel gain. So our data set, which is SI here, which has two components. I mean, SN is the sample, and phi is the angle of arrival and angle of departure. These are vectors, of course. So I mean, every sample we have is basically location, time, and the channel gain. We don't do much with the angle of arrival, angle of departure. We assume those are conditional, are known. We're not gonna estimate those. We're not gonna learn those. So we start with the local GAN, right? So if we have a local GAN, so the first extension here is we use conditional GAN. In my BGAN paper, we use the standard GAN. we assume that we have a conditional sampler that draws an AOD pair from a uniform distribution. And then the generator creates samples given a random input, and this sample is distributed according to the generator distribution with the condition on the phi. And the discriminator is a regular discriminator. It evaluates each sample, it's 0, 1, whether it's fake or not. So this is the local view of every UAV. So at the end, every UAV, and this is not, not very sophisticated, every UAV can have a generator that learned its own environment, whatever it observed over time. So the question we tried to look at is, what if the UAVs now have an air-to-air link among them, assuming that's a sub-6 gigahertz, a stable link, so we don't optimize the resources there. We just assume it's a good link. They can exchange some of those parameters. And how can they apply basically in this scenario? Okay, so the equation of the value function, I did not go through the expression. It's just the same one I showed in BGAN. It's just the conditional GAN. So it's summed up over the K conditions, but there's nothing special about it in this case. So again, so how do we map what we did before to here? So now every BGAN agent is one of the drone base stations. And what we're trying to learn is the location time, the distribution of a location time, a channel gain over the entire space that these UAVs have visited or have served in the past or currently. And everyone has his own local data set. They use a CGAN at their own local data set. And they're gonna collaboratively brainstorm to understand this entire space that they're looking at. It could be reformulated similarly. So the machine learning, the actual BGAN side is the same. So I don't need to repeat it. But of course, here we have a wireless connectivity among the drones. So the graph that I was assuming to be a ring or a given graph is not fixed. So we looked particularly at that. So we first say, okay, we have a UAV structure, which is a directed graph. I is a set of UAVs, and this calligraphic E is the edge, the air-to-air communication links that are seen to be ideal. So there's no errors and so on. And at each iteration, each UAV generates this eta, just a fraction of data samples from its observations. So the first question we ask is, can we quantify convergence? What I mean by convergence is the probability with which my generator spans the entire data set, or in other words, the probability with which I know the entire spatial and temporal map of the system. So, this looks complicated, but I'm gonna go through it. Essentially, it depends, the important part of it is it depends on this Lmax, which is the maximum shortest path in your link. So the probability for a given graph structure of converging in T is a constant number of iterations. These are the iterations to do BGAN, not the local iterations. The local iterations are individual to every agent. So the first observation is your probability of convergence increases when the shortest path is larger, and that kind of makes sense. But it has different options for in different regimes. So if your number of iteration is below the maximum shortest path, then the probability of convergence is 0. This is not an interesting case. It doesn't, BGAN doesn't work in that case. And then it becomes a function of epsilon, which is the local training error, an upper bound on the local training error. It's also a function of this Lmax, which is the maximum shortest path. It's also a function of the number of n-degree UAVs, because again, it's a graph. And it's also a function of this shortest loop path, which goes from a given UAV back to its UAV. So at some point, this appears in the proof we were doing for this. And then at the end, it seems that when you're above this Lmax plus Lmin loop, then your convergence is faster, right? But this comes at the expense of a larger convergence time. So the probability of converging is faster, but you have a larger convergence time. Now, the question was, can we find, naturally, once you characterize this, can you find the optimal graph structure that minimizes the convergence time? Essentially, that's where I'm trying to head towards. So the probability of convergence, again, I mentioned it again, it decreases as the length of the shortest path increases. So I want to try to minimize the maximum shortest path. In
alpha is large, then this probability is going to
in my network. And then the number of iterations required for convergence within a certain confidence level, we call it TG. The confidence level is just a parameter p tau. This is, if you want the iteration after which I'm satisfied and I'm assuming convergence is good enough for me with this confidence level. So we can compute the convergence time, which is dependent on the transmission time in the air-to-air links and dependent on the local error time multiplied by t. So t is number of iterations. This term converts number of iterations to actual time. And that essentially kind of wraps up the convergence. And now I can pose the problem formally as an optimization problem, which is I'm trying to find the optimal graph structure that minimizes the convergence time subject to transmit power constraint, to an SINR threshold, to a transmission time threshold as well. And I need a strongly connected network because I want all my UAVs to learn. And I have I assume number of resource blocks B is greater than the number of air-to-air links. So I'm assuming that you don't have interference over these air-to-air links. Again, these simplify some of the proofs. You can relax the assumptions and look at something more complicated. Now, it turns out this problem at the beginning, at first glance, it looks well formulated. I mean, I have expressions. I can solve the problem in some sense. The problem is this assumes I have it kind of contradicts what I wanted to do initially, which is a fully distributed BGAN structure. It assumes there's a centralized server that knows all these links, has all this information, and can solve this optimization problem. Now you can do that, that can be solved, and you can find the optimal solution. Unfortunately, that's not very practical in this specific use case. So what we try to do is we try to kind of simplify things. So first we said, what if we just take the case where I'm guaranteed that I'm guaranteed that the number of UAVs is the number of air links. So the number of air-to-air links is just equal to the number of UAVs. So I simplify that problem. And in that case, we can show that you can decompose the problem into multiple UAVs, so per UAV problems. So every UAV solves its own problem. And then from there, we show that actually this distributed solution can also work without this, with relaxing this assumption. So the proof is just more on the optimization side. It's not directly related to the learning. But then we also show that once you have this, so what do I have now? What I have now is all the UAVs, they have this their own channel samples. They collected them. Again, the collection process was a simple collection process. And now they used BGAN with a conditional GAN to be able to learn this spatial temporal map for a given graph. Next, what I did is I said, I want to find the fastest way to do this training. So I had to quantify my probability of basically convergence. So I had to quantify that as function of this Lmax and epsilon and so on. And then I mapped that to the convergence time itself, which is function of the time you do to transmit and function on the time to do the local updates, this T epsilon that I had. And then I posed the problem as an optimization problem. Now, this optimization problem can be solved in a centralized way, but we also show that it can be solved in a distributed way, meaning that every UAV can contribute to solving this problem. So you don't need a central server kind of dictating this solution. Again, there's a lot of bells and whistles you can add to the problem. You can make it kind of more sophisticated, but I mean, I think this is a good start to this type of kind of modeling. At the end, what do I have? At the end, what I'm having is that I have now UAVs that somewhat can generate channel gains from the entire space that they visited and that others have visited. So how do you use that later? You can use it in different ways. You can find the empirical PDF, for example, from the samples. You can use the generator itself. I've seen works doing a lot of solutions that use a GAN that's already trained. So here you can just do this as a first step, collaborate, learn the space, and then you can think of other problems to do on top of it. And we show that this distributed solution has a reasonable complexity. It depends on, if I remember well, I think it depends on the number of resources available to your this B actually. And there was, it was, I think, linear, or I don't remember exactly what, but it was a reasonable complexity at least. In this case, again, this is the complexity of this optimization problem, not the BGAN part. The BGAN part is separate, and it kind of follows from the BGAN work. So now, in terms of simulations, before I move, we used some data from a few papers that kind of posted their data on GitHub. So they had some UAV data collection in some urban areas and so on. So we used some of those data sets. So I mean, the simulations are quite intuitive at the end, but I'm gonna go through them a little bit. So I'm showing the probability of convergence and the number of iterations needed to converge. And you can see that I is the number of UAVs, B is the number of resource blocks available for UAV to UAV communication. Of course, I mean, this one is the more intuitive one. If I have a lot of resources, so all the UAVs can communicate, and there's no problem in this, then I have the fastest basically convergence. Now, on the other hand, if you have more UAVs and resources are constrained, and that's the more practical case, then you start trading off your convergence time with, you know, with the amount, I mean, with the need for your accurate channel modeling. So there's this kind of the network size for a given limited amount of air-to-air links you can establish starts to increase your number of iterations needed to train your collaborative GAN network. And then you have this, again, the probability of convergence, and if you have more local samples, so the more local samples you have, again, the faster you can converge. But even if you have a few local samples, you can still find a probability of 1 to converge, and that's kind of good. The other parameter we valid here is the upper bound on the local training error, local basically at every UAV. It seems this parameter does not affect much your probability of convergence, and that's good. That's kind of like some robustness to local training errors. And that kind of comes because we are able to share the different parameters among each other. Now we compared again with the JSD with, so when I say JSD, it really means how accurate is your PDF. We could have plotted some PDF, but the problem is it is multidimensional. It doesn't look nice. It's just, it's hard to visualize. It's easier to kind of compute the JSD and show it rather than that. So we can see that the average JSD, if you're using just your local GAN, so you don't communicate, it's much higher than using the proposed solution. If you have a centralized CGAN, it's of course the best you can do, and ours is not that far off from this, and it's better than FLGAN. It's better than NBGAN as well, which is our other comparison. And here we look at the communication overhead, basically how many bits you need to transmit, number of resource blocks, and again we're better than FLGAN, better than NBGAN in this case. But again, the comparison to FLGAN is a specific. It's on a use by use cases. I cannot make a general statement there. And finally, I mean, if you have a more accurate channel model, you can have a better data rate when you do communication, and that's kind of an obvious result. So this kind of summarizes this application of BGAN in a wireless environment. I'm gonna here now take this quick reroute again because Akash was interested in this work as well. I'm not gonna be very deep in this work, just a glance. I'm happy to answer questions, of course, but I don't want to take like more time. So we've been, I mean, this work is a bit before the one I presented now. So we were thinking a little bit more about reliable low latency and kind of what can we do with it beyond this traditional URLLC, which is again uplink short packets application. So we were saying, okay, what if we're not in uplink short packet? We're more like possibly downlink, possibly you're transmitting larger packets, and you still need them to be reliable. Perhaps not in the strict URLLC sense, but you still need to have some guarantees on the reliability and on the latency as well. And what if we don't have models? We don't have MM1 models. We don't have a rigorous models to actually model the entire latency. And what if, I mean, there has been a lot of use of deep reinforcement learning to do resource allocation in wireless in general, right? So, but in URLLC, the problem is I'm interested in this reliable aspect, which means there could be deep fades or a surge in traffic that a classical deep RL needs time to adapt to, and that's the problem. It's not a problem if you're doing a traditional resource allocation, perhaps, but if you need some reliability, this transition time for your deep RL to actually cope with this change in the environment, with this like extreme event that it has not seen much before, there is a bit of a transition time. So we were really focused on kind of trying to reduce that. And I mean, this first bullet is, I mean, it's just redundant a little bit. I assume there could be some rate guarantees. Now here from this, there's also this idea of what is low latency, right? So what are the numbers do we need to look at? So from this motivation, they span two problems. One I'm gonna discuss, one I'm not gonna discuss. The first one is this experience deep RL for model-free, let's say reliable low latency. I don't want URLLC to connotate to the 3GPP definition because we're not really specifically looking at short packets uplink IoT, although it could apply there, but it's not specifically what we're looking at. The second one really looks at my last bullet, which is when you talk about latency, typically you have a controller in the loop. And ironically, as wireless folks, we've been for a while assuming the controller is just a target latency. Like, you know, this controller has 5 milliseconds. Instead, we actually could model the controller and do joint communication and control. And that's a problem we've been looking at for a while, but it's a little bit out of scope of today. So again, this will be a glance on this work. So it's a very simple problem formulation. We have a single cell wireless network, and we looked at the OFDMA resource block power allocation problem in the downlink. The key though is we have a reliability constraint, which we define to be the probability of end-to-end packet delay exceeding its threshold. We don't use any delay model in the system model. So we assume delay is hard to model, and some of the models are approximate, and let's just assume it's a model-free environment. So the problem itself is really classical. I'm trying to minimize my power over resource blocks, number of users, and over time. And I have this rate constraints, I have power constraints, I have feasibility constraints. Rho is the resource blocks, P is the power control, and the key of this entire problem is this reliability constraint. So prior work, you usually had this probability of D greater than D max, less than some sort of reliability guarantee. There has been a lot of interesting work from many groups, which use Lyapunov optimization, a lot of tools, but they usually have a model here. And with the model, they can, they have a lot of contribution in the sense that they quantify this probability and then do some proofs and find the solution. We assume we don't have a model, so we still want to solve this problem with a model free here and using clearly, it's a very clear motivation to use DeepRL, right? Because we want to have model free. The problem is complex again because of this constraint, and there's a lot of motivation to do that. So what was the DeepRL framework? At the heart of it was a classical deep Q network, and it was combined with a PPO algorithm as well. So we did two tricks. One, and it's not of interest perhaps to today's talk, is we used some optimization tricks to reduce the space, not just the state. Because DeepRL allows me to reduce the state space, but I did something on the action space as well. But what I really want to explain is this idea of what if there's an event that happens that this DeepRL didn't see before, right? So how can it cope with it? Because that maps directly into the reliability, meaning all of a sudden my delay is high. Now, how can I react to that? How can I make the network kind of the power allocation in this case adapt to that? So the idea was to create experience. Now, of course, there has been works where you do DeepRL, you train it offline with synthetic data and you deploy it. What we did is a combination of synthetic, and we said that in reality, wireless networks, we often don't have data sets. Even if they have them, most people don't share them with us. And even when they share them, it's often not the data set you want. So what if I say I have a limited data set that is real, that I obtained from somewhere, and I want to use the models not to model the network, but to generate synthetic data sets. So it turns out that you can do that using a GAN that was proposed by Apple actually for computer vision. They looked at a problem that's a little bit similar to what we wanted. So they had something called the refiner GAN. This refiner GAN, they said we have pictures of eyes, and we have only a limited number of unlabeled real images of eyes looking in different directions. I don't remember if they also had like male and female, but at the end they had like different variants of eyes. And they had a synthetic simulator that can generate all sorts of eyes. So they said, can we create a GAN that's called the refiner GAN, which can use this partial data set and allow us to control the synthetic data set in a way to generate as much data as we wish that is refined, that is belonging to this, if you wish, to this distribution, but also controlled through the synthetic distribution, somewhat of an amalgamation of my synthetic data, which I can control, and of my real data, which I cannot control. So we did kind of something, we applied this, in this case, the paper was focused only on this GAN. So they did computer vision and they looked at it. What we used it for is to train the DeepRL to create experience for the DeepRL in a virtual environment offline, basically having unlabeled real information. For this particular paper, we find some data online on a packet arrival and some channel data. And we have a synthetic data using classical model, MM1 and all those models. And these are input to the refiner. The refiner will refine those data to kind of generate, kind of complement, if you wish, the real data with additional points. And that allows you basically to kind of, in some sense, mimic the extreme events or mimic these events that are rare, but don't appear often in the DeepRL. And then after training, you deploy in the real environment. And I will show a very simple simulation before I conclude. So in this case, we had this, we compared four approaches. One is vanilla DeepRL, which is your traditional DeepRL. One is pre-trained only with the real data, that's the blue curve. One is pre-trained only with the synthetic data, that's the green curve. And one is this refiner-based. What we did is at epoch 100 in this case, we inserted a surge in data traffic. We increased the inter-arrival, the packet inter-arrival time. And you can see that everybody, all the approaches will adapt eventually to it. But you can see how we reduce the transition time. So this red curve is very quick in reacting back to this kind of like unexpected or unforeseen. So from here, I'm just going to conclude with a kind of open view on our portfolio, some of the projects that we have, and I mean, of course, take questions. Sorry if I'm a little bit over time. So of course, we've been doing quite a bit of work on the wireless low latency reliability, going more towards recently sub-terahertz and RIS, more on the, I would say, resource management side and self-organizing networks and so on. We've been doing quite a bit of work also on AI-enabled XR over wireless primarily. And I mentioned this communication and control. And I have a thread in my group looking more on the machine learning side. So reducing the reliance on training, doing more multi-agent systems, GAN in some sense, but I would say that the students working on GAN are on the brink of graduating at this point. So we're kind of pivoting a little bit there. And looking more at beyond federated learning, just a umbrella term to say, you know, more distributed learning that's more reliable and more interesting in some sense. We have a Muri project going on age of information. Primarily, I'm looking in that project at the management of information and its modeling. I talked early on communications for learning as well. We have a small project applying machine learning to actually a city in Indonesia, where we're getting data from their air pollution and also from their garden alleys. They have like these garden alleys. And we're trying to come up to a way for them to kind of recommend crops in some sense. And I mean, of course, always this go back to my roots, which is game theory. So we always have game theory going on. And I had a few MS projects looking at capsule networks, recently more on quantum com, and a while back ago on blockchains. And in conclusion, I think distributed learning is an exciting area. I mean, there's more that I can cover in one talk. And it's not just federated learning. I try to always say that. And it's not just take federated learning and apply it to some problem. That's a good thing to do, but I think has been quite exhausted for a while. I think GANs are very important, and I think this group knows that probably more than me. And BGAN, I think it's one of our first ways to look at fully distributed GANs, and there could be abundant fields of application. Particularly, I think this multi-agent machine learning, which I mean has some roots in game theory originally, is a very interesting area for a lot of us. And finally, I'm happy to take questions